Good morning, students. Today, we are going to discuss about Einstein coefficients in lasers. So this topic is very much important to understand uh, what are the conditions that is to be maintained while you are producing lasers. Or you could question yourself that what are the necessary conditions that is to be maintained while producing lasers. So let us go back to our previous class. If you say laser is nothing but a light, or in other words, a photon has been generated, that means uh, that's the cause that is always accompanied by the effect. So in physics, cause and effect will compensate. Okay, especially in lasers, to understand how come the lasers has been, what are the conditions to produce lasers, we should start with uh, among four transition processes, optical transition processes, we should start with understanding what is the cause for the spontaneous emission process. See, this one is spontaneous emission process. Ultimately, the cause for the emission should be absorption. So, spontaneous emission is followed by spontaneous absorption. Similarly, stimulated emission is followed by stimulated absorption. So, you think like this: spontaneous absorption causes spontaneous emission. Similarly, stimulated absorption causes stimulated emission. Okay, now, for example, if you consider a simple system where in that physical system only two energy levels are there. Energy level 1 is nothing but ground state, and energy level 2 represents excited state. So in addition to that, if you give a notation to represent spontaneous processes with capital A and stimulated processes with capital B, what are the stimulated processes? Is nothing but stimulated absorption and stimulated emission. So in that case, A21 represents spontaneous emission. This is a coefficient of spontaneous emission. Similarly, A12 represents spontaneous absorption. The same way, B12 represents stimulated absorption, and B21 represents this one. B21 represents stimulated emission process. Have a look here. We have capital N subscript 1, N1. That's nothing but number of atoms that are available in the ground state or lower energy state. Similarly, N2 represents number of atoms in the excited state. Okay, how many excited states are there? Among four optical transitions, there are two excited states. That is spontaneous emission. In spontaneous process, there is one excited state. In stimulated process, there is another excited state. Okay, anyway, here you will see another notation, that's rho of R is nothing but energy density. We use in the case of absorption That's the energy absorbed by the system. Similarly, same rho of R we use. That's the density of energy that has been emitted by the system. Okay, don't get confused. We are not, no, we would like to give a simplified notations so that we can minimize the complications in rho of R. So, in both cases, rho of R represents density of energy. Okay, now here is the condition. The entire derivation of this topic is based upon by assuming the physical system is experiencing thermal equilibrium condition. So what do you mean by thermal equilibrium? There is nothing but, if the absorption, the rate of the absorption processes becomes equivalent to the rate of the emission processes happens, so that physical system will be referred as the system is in thermal equilibrium. Okay. Under that condition, we would say the rate of upward transitions is equal to rate of downward transitions. So what are the upward transitions? Is nothing but absorption. So this B stands for stimulated, 1, 2 stands for absorption. So only this process is upward transition. So remaining A21 and B21 is emission processes or downward transition. So the first equation that you are seeing represents on the left-hand side, it's upward transition. Two terms on the right-hand side represents downward transition. Okay. So if you simplify that expression, subjecting to rho of R will give us this expression. Furthermore, you could divide this expression numerator and denominator by using N2. Furthermore, you could simplify it like that. See, A21 by B21 whole divided by B12 by B21 multiplied by N1 over N2 minus 1. That's the rho of R that has been derived by assuming the physical system is under thermal equilibrium condition. Okay. So now what we have derived can be equated or can be compared with the experimental data done by the Plancks in the case of black body radiation, where, if you don't know, if you say black body radiation, it's nothing but, lossless, or you could say it's a 100% emissivity, all that. Okay, in our case, if you assume that the system that has been built up by us uh, will represent no loss while absorption or emission processes, so that can be equated with the black body radiation law. So in the black body radiation law is the density, the energy density can be represented with rho of, let me show you that value. Next slide. I want to go to next slide. Have a look on this equation. According to Planck's law, black body radiation, you have this rho of nu is equal to 8 by h nu cube by c cube multiplied by 1 over exponential h nu by kt minus 1. So this equation is a proven and experimental equation, which can be compared with the derived equation that has been shown in the previous slide. So when you compare these two equations, I mean equation 8 and 9, what you can conclude that A21 by B21, that means the ratio between spontaneous emission process and the stimulated emission process should be equivalent to the 8 pi h nu cube by c cube. What is that nu over there? It is the frequency that has been emitted by the lasing system. C, that's constant speed of light. 8 pi and h is a Planck constant and pi is a constant. Remaining all are constants. Expect nu. So you put that equation 10, you could express in other words, something like, if you bring B21 to the right-hand side, that's stimulated emission process will have a multiplying factor, that is 85 h nu cube by c cube factor. You could say this is the multiplying factor, or a factor that represents the amplification of light that has been, amplification factor uh, more than the amount of the energy that has been seen by means of spontaneous emission process. So we will say that stimulated emission process will have a greater amplification rather than the spontaneous emission process. The equation 10 itself represents the definition of laser. What is that? LASCR stands for light amplification. See, the definition itself says amplified light can be achieved by means of stimulated emission process. So here B21 represents stimulated emission. Okay. So let us come to another conclusion we have got in terms of equation 11. That is what throughout the experiment process, you have to maintain B12 by B21 is equal to 1. What does it mean? B12 is equal to B21. Furthermore, what does it mean? Stimulated absorption, the rate of stimulated absorption should be maintained equivalent to the rate of stimulated emission process. So this equation 10 and 11 are very much important if you would like to produce lasers. Okay, with this conclusion, I would like to stop. Let us meet you in the coming lecture. Thank you, students. Okay.